Alright, so now we're going to talk about sampling distributions. This is kind of the final frontier of everything we're doing here now. We're going to talk about what the sampling distribution is. We're going to talk about the difference between two types of sampling distributions. We're going to determine the two major theorems, the laws of large numbers and central limit theorem. And we're going to use the normal curves to determine probabilities about sampling distributions. A sampling distribution is a range of all possible outcomes around a statistic. So I kind of think of it like this. So let's say that that we know that overall 13% of people are left-handed. Well, just because we know that doesn't mean if I take any group of people now, it'll come out to be 13%. What we might get is a range. So like I might take a group of 60 people and it turns out that they only have 12% left-handed. Or I might take another group of 60 people and they might come out to be 12.5%. So what you do is for the sampling distribution is it's literally a distribution of all of these possible possibilities, which should center at 13%, which is our population parameter. Now, you can think of this as similar to a probability distribution, although it's slightly different for a probability distribution, but it is they're similar to each other. We have two types of sampling distribution, one for means and one for proportions. Really, it's kind of like one for quantitative data and one for categorical data. But we'll get to that in a second. Okay, so according to a new study of Maryland teachers, about 38% of them are satisfied with their current pay. Suppose that we take a random sample of 500 teachers. We want to create a normal sampling distribution for proportions before we do this. We have to prove that we can do it. So we're going to take a normal sampling distribution of the teachers based off this information, based off of 500 teachers. And essentially, we kind of want to know what we are going to expect. But before we do that, we're going to prove that we can do it. There's kind of two rules that we use to prove that we can do it. One is basically telling me if it's large enough. Now, we have these two theorems. The first theorem states that, and it's called the law of large numbers. And this theorem here basically is a thing that when you go to insurance people, this is what they use to determine what your deductibles would be, because it bases you off of the large number of people in your age group or in your demographic or in your health range where you would be likely to die or whatever you're trying to get your insurance in. So that's where you get your premiums from. So the large number states as we obtain more and more data, the average of the sample approaches the true average of the population. So basically, the average of the sample is X bar. The average of the population is mu. As we collect more and more data, this should get to be this. At some point, they should be equal. Then we have the central limit theorem, which states after a certain amount of data, your data always forms a normal curve. After a bunch of data. So basically, what qualifies these two things to happen? Well, the very first thing is that you take your sample size and multiply it by your probability or your proportion. And it has to be greater than or equal to 10. And you take your sample size and multiply it by 1 minus p, and that also has to be greater than or equal to 10. And now, we also want to make sure, really this second rule should be over here. So the second rule, I'm not quite sure why I wrote it over here, to make sure it's a good sample size and it gets those rules, is to show that the sample size, it can't be too big and it can't be too small. So we have to show that the sample is less than 10% of the population. To do this, we take the sample, we multiply it by 10, and show that that's less than the total population. Now, we also want this thing called an unbiased estimator. I don't know why I'm just highlighting it all. I'm just doing it. So, because we don't want it to overestimate or underestimate a statistic. The way we do this is to employ this standard error formula, which is kind of our standard deviation. So standard error basically is equal to standard deviation. And our standard error formula is the square root of 1 minus p times p over n. So how does this all work? Well, going back to our situation here, we want to find out this sampling distribution based off of our Maryland teachers. So what we do here is first see that we can do it. So this is our p, and this is our n. And so what we want to do is first we want to show that it's not too big, or show it's not too big by doing 500 times 10, and we get 5,000. And what we say is 5,000 has to be less than all the teachers in Maryland. So 5,000 is less than all teachers in Maryland. And I don't have the data to support that right now, but in the place that I work, there's probably, or in the county that I work, there's probably more than 5,000. So I'm willing to believe that in all of Maryland, there's much more than 5,000 teachers. So then I'm going to do 0.38. So now I want to see that it's not too small. 0.38 times 500. So I do 0.38 times 500. That gives me 190. And that is definitely greater than or equal to 10. But then I'm going to take this number and do 1 minus 0.38. So I get the opposite probability. 1 minus 0.38 is 0.62. And then I want to multiply that by 500. And so that'll give me 310, which is greater than or equal to 10. Okay, so these two combined tell me it's A-OK, like the Fonz. A. Okay. Bad joke. Okay, so from there, I want to actually create my distribution. So central limit theorem says it's going to be normal. And the law of large numbers says once it gets big enough, it's basically going to be the same as the population. And so by doing this, we said it was large enough, so it's good. And then from there, for our standard deviation, we want to do that formula we had, 1 times p over n. Well, let's see. 1 minus 0.38 times 0.38. And then our n was 500. So let's see. That gives me 0.0217. That's our normal curve. And that's our sampling distribution. Okay. So going to the next one, let's do the exact same thing. Approximately 60% of all college students in America are female. What would a sampling distribution of 600 college students in America look like? So, if I do my sampling distribution stuff again, I get first we'll say 600 times 10 equals 6,000, which is less than all college students I guess I should say all female college students, which I'm actually willing to believe. And then I got 0.6 times 600 gives me 360, which is greater than or equal to 10. And then 0.4, which remember this is 1 minus 0.60, times 600 equals 240, which is greater than or equal to 10. And then, oh, not there yet. Something I did today with my class. But so we got that. So then we've proven that we can do it. So we're going to have a normal curve, 0.60 as my mean, and then the square root of 1 minus 0.60 times 0.60 divided by 600. And when I do that, I should get 0.02. Okay. So that's my standard deviation, or my normal, that's my sampling distribution. Okay, we got that. Okay, so now we're going to change things over, because now, and I know this is absurdly wrong, so don't write a message saying how dare you. Free range cows can produce about 500 pounds of beef with a standard deviation of 25 pounds. We take a simple random sample of 400 cows. So here's the difference, and we're calling this a sampling distribution of means. If you look at this, this is going to be my mean. It's not based off of a percentage. Okay, and also it has its own standard deviation because it's the standard deviation of the population that we're then going to create into the sample. So this one's much different than what we did before. So it really has no proportion, it has no percentage in it. Therefore, this one's going to be different than what we did before. A lot of things are similar to the proportion ones we just did previously. Some things are different. The big total is, since we can't have a proportion, we can't do the n times p, which is greater than or equal to 10, and we can't do the n times 1 minus p, which is greater than or equal to 10. So we replace that 1 with n is greater than 30, and this is now our standard error formula. So it switches from the square root of 1 minus p times p over n, which we can't use anymore because we don't have a p. So we'll work like this. We still say 400 times 10 equals 4,000, which is less than all the cows in the world. And then we have 400 is greater than 30. Both work. So it's a nice normal curve now. So we're getting normal, 500, and then here's going to go, my standard deviation is 25 divided by the square root of 400. So that comes out to be 1.25. And that's my normal curve for that. Okay, second example. A random set of 81 people in the U.S. were measured, and it turns out that the average height is 66 inches with a standard deviation of 5 inches. Find the sampling distribution. So, once again, we need to prove that we can do it. So, 81 times 10 is 810, which is much less than all the people in the U.S. The black one's starting to die out on me. Let's switch colors. That's sad. Okay, and then 81 is greater than 30, so we're good there. So we have normal, 66, and then here would be 5 divided by the square root of 81, which comes out to be 0.5556. And that's my sampling distribution. A lot of people say they like this one better because it goes much faster. Okay. And the last thing you do is kind of to look at some probabilities on them. So according to a new study of Maryland teachers, about 38% of them are satisfied with their current pay. Suppose that the random sample of 500 teachers, we take a random sample of 500 teachers. So if you quite remember, back to the other one, our sampling distribution look like this. So what we're going to do here is, first off, note this only works for 500 teachers because we base this off of 500 teachers. If this number changes, then we got to change this because then the standard deviation is going to change. Then what's going to happen here is I want to figure out what the probability of having 35% of them satisfied. Really, I can't do 35%. It has to be 35% or less. I should have caught that. But 35% or less. So I'm going to go do my normal curve stuff, which, again, my students love to do it in StatCrunch. When I go back over, I'm going to do several examples both in and out of StatCrunch. But the mean is 0.38, 0.0217, and we're going back to standard, and we're going to be less than, it said 35%, so we're going to do 0.35, hit compute, and so the probability of that happening would be 0.0834, or 8.34%. Okay. And then you can just perform any normal curve stuff that you would possibly want on that.